Guys, you ready to roll?
All righty. Good morning. Welcome back, everyone. So we're talking about photosynthesis this week, and mentioned how photosynthesis is extremely important for crop production, of course. And basically, what we're trying to look at from a practical standpoint is how do we get our plants to photosynthesize more? How do we maximize photosynthesis? And that really deals with just getting that light to the leaf canopy. So depending on what type of crop it is, we might do that by eliminating other canopy around it, making sure that crops are grown in full sun where it's possible. Also, the arrangement of crops in rows. So at our latitude, generally we want to orient our crops north-south so that they're not shading each other out as they're growing. So it's another way to maximize that photosynthesis, which in turn is going to maximize the sugar production, maximize the harvestable part of the crop itself. Of course, we have to have carbon dioxide, and in closed growing situations, we might try our best to increase carbon dioxide, potentially in a greenhouse or nowadays in a lot of these artificial growing situations where they're growing crops even in trailers, very closed environments. We have to inject that carbon dioxide in order to be able to get that in there to actually maximize photosynthesis. The other thing is water. We have to have the right amount of water for photosynthesis to take place. And it's partially through that, whole conduit of the plant where the plant is absorbing water from the soil, it's moving it through the plant, and then eventually through and out of the plant through the stomata on the underside of the leaves. That respiration and transpiration leads to the growth of the plant. So it's not necessarily just we need water for plants to grow, but we need water to drive respiration and photosynthesis so that the plants can release the gas and release the extra water in order to actually have photosynthesis happen at the rate that we need. So speaking of water, we're going to talk about water relations for crops today. And how we get water to plants partially, and what water does inside and the plant as well as in the soil. So starting off, water is, for most plants, up to about 90% of the plant's mass. In some cases it's more, like leafy greens, for instance, we're talking 95% plus of that plant is water. So if we were to actually break down what a plant is after it's become completely dry, after we've dried it out in a dehydrator, say, or an oven, we removed all that water that's in the plant, we're left with 10% or less of that plant's body. And most of what is there is carbon, hydrogen, and oxygen, with some of our macro and micronutrients in much smaller quantities. But about 96% of a plant by dry weight is going to be carbon, hydrogen, oxygen. Again, that's coming from the carbon in the soil, the carbon dioxide in the soil air, as well as the atmospheric air, and water, which is taken up and fixed into the body of the plant. So often what's left is cellulose, which is carbon, hydrogen, and oxygen in different forms. We get a little bit of nitrogen, phosphorus, potassium, and some of the micronutrients as well. So water, of course, is required not just for a plant to grow and to, make, the photosynthates, but it's also required for the plant's life to begin. It's required for seed germination. We have to have the right amount of water in order to get the seed to actually start taking up that water, and then catalyze water to start creating proteins and the enzymes that allow the embryo of the plant, that baby plant, to break through the seed coat. Water also serves as part of that plant's structure. That vacuum of the plant being the conduit, taking water, moving it from the soil through the roots up through the plant and throughout the leaves, that whole process keeps the plant turgid, keeps it upright, as well as provides that turgidity in the cell walls themselves. That it's a major part of the cytoplasm. So it's required for a plant to be able to just stand up. It also carries the minerals into and throughout the plant, transporting the photosynthates and the biochemicals. Water also can cool the plant through evaporation and transpiration combined into evapotranspiration. If we don't have enough water, then the plant growth and development is going to be inhibited, starting with just a reduction in photosynthesis. Eventually we get to where the plant begins to wilt. It can no longer maintain that turgidity. And if it's great enough, we will reach a permanent wilting point and the plant will die. And almost all the water that the plant takes in comes from the soil through the roots. We do get a little bit that can be absorbed through the leaves as well. And water on the leaves is also important to cool the plant through evaporation. But generally, we're taking up that water from the soil itself. So water has some unique characteristics that allows it to be life juice, pretty much, what I think of it as. First, water is the universal solvent. It can basically dissolve more substances than any liquid. And when those substances dissolve, they become part of a solution. So water helps to dissolve it. It becomes part of that water. At that point, no longer is it just water. It's a solution with whatever it has dissolved in it, which includes nutrients for plants. Water is also one of nature's most stable compounds. And for a long time, before we had a strong knowledge of chemistry, water was considered a single element rather than a compound. And now, of course, we know that it is indeed a compound. It's multiple elements, 2 atoms of hydrogen connected to 1 oxygen atom to make a molecule. But the reason it was thought that it was a single element is just because it's somewhat difficult to break up water, from hydrogen, oxygen. So that's partially due to this unique arrangement of the hydrogen and oxygen atoms to create the water molecule. The molecule itself is not symmetrical. It has this unique arrangement where there's 105 degrees between the 2 hydrogen atoms. And because of that, that lack of symmetry is able to, basically create this molecule with a positive charge on one end and a more negative charge on another end, which allows it to link together with other water molecules or to be that universal solvent and link other molecules to it. So we look at this water molecule here. We look at just the arrangement of electrons. So the red is looking at the protons of each atom. In hydrogen, there's just 1. And oxygen, we've got 6. And we have what are called shells or valence shells of electrons. And the outer shell of oxygen has 6 electrons. For that outer shell of electrons to become stable, they're always searching to have a full set, which is 8 electrons. So it bonds perfectly with hydrogen, because hydrogen is sharing one of its electrons with oxygen here, creating what we call a covalent bond. That's part of the reason why water is somewhat difficult to break up into atoms, because it creates this stable bond with the 8 electrons in that outer shell there. Now, water also has a unique physical property of surface tension, and that's basically due to the intermolecular attraction, the hydrogen bonding between the water molecules, allowing them to stick together. And they basically create this film, this water film on the top, where these molecules are inwardly attracting, and results in this strong tension of the molecules, often like a greater density there at the surface of water. And so we could look at some animals as an example of that. This is the fisher spider, and even though it's a large arachnid, it's able to actually exploit the surface tension by distributing its weight outward and basically gliding on the surface. The fisher spider, as it glides on that surface, on that surface tension, it will contract and put all that weight kind of in the center of its body, so it can go underwater and actually catch fish. Kind of a crazy thing, but we have several organisms that are able to exploit that surface tension. Surface tension is important for these organisms. It's also important for how water is held in the soil. Water is also unique in that it's the only molecule that readily exists in 3 different phases, and all in liquid, solid, and gas. In the liquid state, the attraction of the water molecules is somewhat random and chaotic. So it's kind of like more of a randomized molecular structure of the hydrogen bonds as it's moving, right? It's constantly in flux. But as water freezes, it will create a very symmetrical and therefore rigid lattice. However, it has an open porous structure. And so it's interesting, and that water is the only molecule that, when it exists as a solid state, it actually has less density than it does in its liquid state. So, put some ice cubes in a glass of water, and as they melt, it's not adding more mass to it, it's just the density. It becomes more dense as water. So that, glass of water isn't going to overflow as the ice melts. It's just going to increase in mass and basically just fill it up to the top. So it reduces in density, but increases in volume as water becomes solid in ice at freezing temperatures, which is also what we get, in frost, that basically that freezing, it causes an expansion of it, but the density is less dense. Water also has an unusually high specific heat as well. If we look at the boiling point of water, when it turns into a gas, when it vaporizes there, we're looking at 212 degrees Fahrenheit. So above 32 degrees, we're looking at liquid water, nearly 180 degrees in temperature rise that causes the water molecules to turn into a gas phase. This high specific heat allows water to absorb large amounts of heat without a large increase in temperature. And we can actually use that concept of that high specific heat to influence microclimate in growing situations. We have more water present, that becomes thermal mass, and once the air temperature is below that of the water temperature, it will diffuse that heat back out into the air, causing a warmer microclimate. We do that actually a lot to try to get, say, like fruit trees to develop into flowers by planting them near, say, a water tank. Or also the same concept works, and just think of it like a brick wall, for instance. It absorbs heat, radiates it back out once the air temperature is below it. And water can do the same thing, except water can actually absorb a lot more heat than a solid wall. So looking at the phases of water here, generally we have higher intermolecular forces, basically due to that rigid lattice and that strong structure as a solid. And that looks something like this over here. Solid ice, it makes a very rigid structure. In liquid state, it's more kind of random. It's moving, it's flowing. The water molecules are still close together, but they're able to move around. In the gas phase, we have very little intermolecular forces, because basically the molecules are separated, and they're moving around very quickly and randomly, and they're much further apart, so they're not bonding as well. And in the gas form, water becomes very important. When it transpires and then evaporates, then we're having water turn into these fewer molecules kind of moving around much more quickly, and much easier for them to rise. As they rise into the atmosphere, basically water as a gas is also clouds. I mean, clouds are basically just bodies of water floating around, and the way that they diffuse light causes them to look white to us, but really they have no color. It's just the way that light is being reflected through those clouds, through bodies of water, basically. And the way that clouds work, of course, is that once they become dense enough, then it turns back into liquid water and it falls from the sky. If it's extremely cold and more dense, then it turns into snow or into hail and falls as ice. And of course, clouds have unique properties based on their shape, which is really just based on how those water molecules are connecting and where they're existing in the atmosphere. We're talking about water in the soil. We have to look at how it is held in the soil. And generally, that's what we want to look at. We want to store water in the soil to make water available to plants. So water can basically exist in both the macropores and the micropores in the soil. Macropores being the larger ones that generally drain very quickly, the micropores being the very small pores held within the soil particles that are able to hold on to them much longer. As it moves through the soil, it becomes the solution, the soil solution. And it's containing mineral nutrients and oxygen, as well as just water molecules all stuck together in that solution. So the pore spaces in the soil are always either going to be filled with water, air, or a mixture of some air and some water. When all of those pores are filled with water, then we say that the soil is saturated. And saturation, exists. We see it whenever we have lots of rainfall. Once the soil can no longer store water, it begins to run off rather than actually infiltrate into the soil. If that saturation lasts too long, then that's a bad thing for plants. We can have too much water as well as too little. And basically what's going on there is it becomes unhealthy for plants because it's replacing the oxygen that is needed for the respiration in the roots. roots don't have oxygen, they don't have air pockets in the soil, then basically they can't take up minerals. They also can't even take up water, which is kind of a funny thing. It's like being on the ocean. There's lots of water around you, but you can't drink any of it because it's salt water. But in this case, it's just preventing oxygen from being able to allow the roots to breathe, pretty much. And that concept of the roots breathing is also includes them taking up water and mineral nutrients. When the pore spaces are filled mostly with air, then we have soil that is too dry for good plant growth. So ideally, when we were talking about it earlier, when we started to talk about soil, we look at that, 50% of the soil being mineral and organic matter, the solid portion of the soil, and then the other 50% being air and water, the pore spaces themselves. But really what we want on an agricultural basis to have good crop production is we want that 50% of air and water to be split between air and water. We want about 25% air and 25% water to have plant available water. If it's all water, then that's actually not able to be taken up by the plant. So we look at that in terms of the number of pores, which is going to vary with the soil's texture as well as the structure of the soil. When we talk about a soil's ability to retain water, we refer to that as its water holding capacity. Makes sense, right? So here we're just looking at two different soil textures. On the left here, we've got a sandy soil, and on the right, we've got a heavier clay soil. And in both cases, we have this kind of same thing going on where the soil is wet, and basically as that water moves through this, the pores in the soil, it's going to move very quickly through a sandy soil because they're macropores. They're larger pores because the size of the soil texture of sand is very large, and it has a lot of space in between those structural components, those little pieces of sand. So water drains very quickly. In the clay soil, we have more micropores, and actually there are a lot more. Even though we think of sandy soils as being very porous, we actually have more porosity in a clay soil, but they're much smaller. So it takes longer for the water to move through the soil. And it's going to do this through a wetting front. So water is going to basically first drain gravitationally. It's just gravity is just going to pull the water down. But it doesn't just go down, it moves throughout this wetting front horizontally, in some cases even up vertically, diagonally through these pores. So it's moving from an area that is wet to an area that is dry, and that wetting front often is going to have kind of more of like a teardrop shape. So generally we have higher clay content, we have higher water holding capacity. Same with organic matter. Here's just a look at the water holding capacity in terms of time with different soil particles. Sand generally it's going to drain most of the water within 1 day pretty much. In a silty soil, a little bit slower. And we have more of that water retained long term, and a clay soil even longer. Often in heavier clay soils, it might be dry to the point to where we have plants starting to wilt, but it doesn't mean there's not water in the soil. It's just not available to plants because it's so tightly held to the soil particles in the micropores. So we have three forces of water movement within the soil. First, we have gravity, which is just the pull of water by the forces of gravity, generally downward, although through the pores can also be horizontally as well. And this is the principal force of the movement of water when the soil is saturated. We also then have adhesion, which is the force of the attraction between unlike molecules. You think of adhesion like a magnet or like super glue holding the water molecules to the soil particles. And in some cases, we've got chemical bonds that have a lot of force that are basically holding them very strongly to those soil particles. Then we also have cohesion, which is the force of attraction between like molecules. So we have water sticking to other water molecules. And these two forces, adhesion and cohesion, together allow water to move through what we call capillary action. And think of capillaries just like we have them in the human body as ways that move liquid. In us, it's blood and plasma, but in the soil, it's water pretty much, and that movement of water, fluxing between water and air. But adhesion and cohesion together, first water being attracted very strongly to the soil particles, and then a little bit less strongly to each other. They're able to move basically in any direction. Through capillary action, we can have water actually moving back towards the surface, moving upward against gravity. They can move downward, they can move laterally, and these are the principal forces that allow water to move in an unsaturated soil. So after that water is drained away from gravity, we've got, it's no longer saturated. What is left at that point is plant available water. It has to move through capillarity to the plant's roots to actually be able to be taken up by plants. So here's just a demonstration of capillary rise, and in this image basically depicting that on one strip we've got some blotter paper, and it's inserted partway into the water with these capillary tubes. And as the soil dries, the water film surrounding each soil particle is going to thin, and it's going to allow that water to move up the gradient. So the adhesive and cohesive forces together are going to increase rapidly, making it more difficult for the plant to extract water that is held tightly to soil particles. And we can actually depict this very easily by taking paper towel, putting some dye and some water, and allowing 3 containers, have one yellow, one red, and then watch it as that water moves up that gradient. The pores of the paper towel are very similar to the pores in the soil. It's going to move up, be absorbed, and then will actually move back down into the other water and cause, what is in the center to be orange. Kind of neat. So forces that act on soil water create changes in energy, and this energy of the movement of water is water potential, and we look at that in terms of pressure. So we use the Greek letter psi for that. Water potential is going to determine the direction at which water is able to flow. And it's always going to be from high to low water potential, from high pressure to low pressure, from wet soil to dry soil. And we use units of pressure to measure that water potential. Generally, we use the megapascal or kilopascal to measure that pressure. If we have saturated soil, all of those pores are filled with water, and we have a relative humidity of 100%, then water potential in the soil is going to be 0. And I know 0 is nothing, but generally we say that's a high water potential. As water drains away, that soil water potential is going to decrease and become more negative. When that negative potential exceeds the gravitational pull, then water no longer drains and it's held there in the micro or macro pores, generally more in the micro pores. We determine soil water potential by several different factors. First, just gravity itself, moving it downward. Then we have the matrix potential, which is basically more of the plant available water. That's resulting from adhesion and cohesion between the adhesion of the soil particles to water itself and the cohesion of water molecules, to other water molecules. We also have osmotic potential, which is not as common. It does exist though, but it's caused by dissolved salts in soil water. And generally we get that more in irrigation, where, unfortunately, as we move water, it has higher likelihood to absorb salts. Or as we fertilize fields, often we're, adding fertilizer that is, these nutrients are bonded to salts. So in a way, we're, salinizing the soil. So we look at irrigation water here. Generally, we got an irrigation canal. I'll say that this is in, let's just say, Central California, where we have very important agriculture. And it's happening in a very arid place. So they're, basically taking water, moving it through these sophisticated canal systems and into furrows in between rows and fields. And so that water is going to move first downward. Gravity is going to pull that water down through that canal. But then the matrix potential, those combined forces of adhesion and cohesion, are going to allow that water to move laterally through the soil, which causes this to be kind of more of a teardrop shape and moves that water to the plant roots that are in the row. So even though that water is at a lower area than the plant, say that our rows are mounted up to be a little bit higher than the furrows, the ditches where the water is being irrigated into. Basically, it's still allowing it to move laterally, but also upward to those roots, so that the plants are actually able to absorb the water and grow our crops. We have salts present in some cases in soil naturally, and it can be present in soil water, which causes it to create this osmotic energy and basically moving water through osmosis. If we have enough salts, then it can actually prevent water movement into the plant. So the graphic here, we're looking at the beaker A there, like a celery stalk in it. We have salt water in there. So it creates an osmotic pressure that is too great for the plant to overcome. So even though it's sitting in water, that water is limited in availability. It can't overcome that pressure gradient to absorb the water. And basically that plant will wilt. Pure water, then it's readily available to the plant and can absorb it. So salts generally are a bad thing. And when we over fertilize, you might have seen this at some point in your, say your grandmother's house plants, right? She, fertilizes with, say, Miracle Grow. Salt will actually cause water to move closer through that osmotic potential to the soil surface and evaporate. With that, it carries the salts up. So you have salt accumulation at the top of the plant on the soil surface. So we get that, in house plants a lot because they have a very small area of, soil zone there, and it's basically able to move those salts up quicker. We'll also see it in containerized plants in our greenhouse, for instance. We have salts naturally unnaturally in the water, added to the water to treat them. Chlorine and fluoride existing as salts. They will accumulate as a white, almost chalky substance there at the top of the soil through this osmotic potential. I've already said it a few times, but fertilizer is a salt. It's often bound to salts, synthetic fertilizer anyway. Generally, our more natural fertilizers, our manures, those are not, salts. So we can get, fertilization without it being bonded to salt, but generally the vast majority of our synthetic fertilizers are bound to salts. And over-fertilization can inhibit water uptake due to that osmotic potential. And if we allow that fertilizer to build up, then we have to flush it with pure, fresh water in order to get that salt to move back down and eventually run off. It can lower the water potential enough to pull water out of roots in some cases, which causes damage, which we often refer to as fertilizer burn. But it's basically just that osmotic potential drawing water to the salts rather than to the plant's roots, or in some cases we get this fertilizer burn on leaves as well, where we've applied fertilizer to the tops of plants. So burn is not actually just it's not actually physically, increasing the temperature of the plant itself. It's just drawing the water out. So here's an image looking at soil after either prolonged rain or irrigation. In A, we've got saturated soil. So all of the pore spaces are filled with water, and that tension needed to remove the water, that pressure, is going to be zero, basically, if we have high humidity. In B here, we start to see water draining away. The air to water ratio becoming larger, air occupying more of those pockets. And at this point, we get field capacity, where we start to get a closer air to water ratio after all the gravitational water has pulled the water that it can away. And this occurs at about 1/3 of an atmosphere, 1/3 of a bar. I should say it should be negative 1/3 there, is the atmosphere at which that pressure gradient, this is plant available water between field capacity. As the soil continues to dry, plants are taking up water, from these pore spaces. That water film is going to become thin, and it's going to basically be very highly adhered through adhesion, adsorbed to the surface of these soil particles. And at that point, extracting that water requires a higher tension. So at this point, we're looking at like -15 atmospheres. So we would need, basically a larger amount of tension, of pressure, to be able to absorb that water. That's more than most plants are able to exert, which causes plants to wilt temporarily, and eventually, if that airspace is not filled with water again, and it gets to field capacity again, then the plants will wilt permanently and die. So again, looking at the soil texture, determining that soil water content and that pressure gradient. So the clay soils are able to absorb more water, but they also have higher pressure. So even though the water content is greater, it takes more energy, more tension to be able to extract that water from those pores in the soil. So the water is there, but is it actually available to the plants? Perhaps not. So soil moisture content at which a plant wilts and cannot recover is called the permanent wilting point. And basically, we're looking here at, we got saturation. If saturation continues, the plant will die, sorry. It will drown basically from having too much water. It's got water, but it can't take it up because it doesn't have oxygen. In gravitational water here, that water is not really available to be absorbed by the plants. We have plant available water existing between filled capacity and the permanent wilting point. So even though water is available, it might not be available enough to keep it from wilting. Generally, the closer we are to filled capacity, which is where that ratio of air to water in the soil is, closer to that, 25 to 25%, closer to 1 to 1, we have that pressure gradient that allows water to be taken up by plants. They don't have to overcome great pressures to actually absorb that water. So beyond a certain point, there might be water in the soil, but that's beyond the permanent wilting point. The plant will die from not enough water. If the soil becomes air dry, all liquid water is gone except that is held as a very thin and very tightly bound layer, a film around the soil particles. And basically, as we see here, that pressure increases to very strong amount. So the adsorbed water held just the soil particles is called hygroscopic water. And we're looking at about -50 atmospheres of tension that is basically impossible for a plant to overcome, any plant. And then as it even gets further, we can have it up to -10,000 atmospheres. So there's no way that, really anything could extract that water. And that causes water actually to become a crystalline lattice structure that's actually becomes pretty much part of the soil structure itself. So available water we're looking at as soil moisture between filled capacity and the permanent wilting point. It's not really available between filled capacity and saturation because all of that is lost through drainage. It's subject to the forces of gravity. It's moving too quickly for plants to be able to actually absorb it. At tensions that are greater than the permanent wilting point, it's held too tightly and plants cannot overcome that pressure. So we want available water to be closest to filled capacity for plants to be able to actually take it up. We want just enough water, not too much. So water is absorbed by the roots from the soil and then distributed throughout the plant to its highest concentration in leaves, which there's still a pressure gradient taking place there. It's going to enter the xylem inside the plant through active and passive forces. The upward movement of water occurs mainly through the xylem, which are these dead cells, as we mentioned earlier. And once in the xylem, the potential or tension is going to decrease from the root to the stem, to the leaves, and then eventually to the air through the conduits of the plant. The minerals that are dissolved in the water in that soil solution are also carried to the leaves, stem, fruits, and roots through the xylem stream as well. So here we have it moving as a decreasing water potential from the soil through the plant to the atmosphere, creating the tension or turgidity in the plant through a cohesive chain of water molecules, water sticking to water, moving through that xylem tube in the plant, and then eventually into the leaves, and then through the stomata, those pores on the underside of the leaves, and out into the atmosphere. We call that water flow from the roots to the leaves the transpiration stream. And that pull, that kind of vacuum, is created from the outer surfaces of those mesophyll cells, which basically just a movement of water across that gradient. The evaporation of water from the leaves is one of the most, say evaporation, but has to occur as transpiration. So really evapotranspiration of water from the leaves is one of the most important ways that a plant is able to regulate its temperature. It's just like us, we sweat. Really the same deal. We're regulating our body temperature by, moving water through our pores. It's the same thing with the plant. if we don't have enough water available for plants to take in, then the stomata will close to conserve water. And that's why desert plants such as cacti and succulents can survive under these hot and dry conditions. As we talked about on Monday, they go through that CAM pathway of photosynthesis. So they're able to open the stomata at night when temperatures are lower and less of that water vapor is just sucked out by dry air. So osmosis, we kind of started to talk about that with the osmotic potential. It's the flow or diffusion of water that takes place through a semi-permeable membrane. And that's going to happen in the plant as well as in the soil, in salty soils. So it typically is going to separate a solvent and the solution. So it's going to remove the minerals from water, go from a dilution to more of a from a concentration to more of a dilution. These concentration gradient differences create the flow conditions through the semi-permeable membrane, and as equilibrium is established, osmosis ceases. Some water, as I mentioned, is part of the plant structures and is actually held in that fluid in the plant, the cytoplasm. And some of it is used for biochemical processes. Some of it is stored in the tonoplasts inside the cells of the plant. The high volume of water inside the cells is what creates that turgor pressure, giving the cells its rigidity, giving the plant its ability to stand up. If we have insufficient water, we lose that turgor pressure and the plants will. So generally our minerals, they're moved through water. If we think about it in terms of starting growth of a plant, then we have those minerals stored by the seed, but it's water that basically allows the catalyst of those nutrients to become available. Any additional nutrients have to be absorbed from the soil. And it's the plasma membranes of the cell that are largely impermeable to the movement of ions, so energy is required to move those ions against that concentration gradient through the impermeable membranes and actually to absorb those nutrients. Plants are able to absorb these mineral nutrients against a very high concentration gradient through active transport that is facilitated by proteins in the plasma membranes, actually taking these nutrients and moving them through that membrane itself, which we have to have water to be able to create those proteins. Looks something like this. So this is an example of a potassium ion. So in the energy requiring step, a protein here that is in the actual plasma lamella here, this semi-permeable membrane, it acts as the carrier. It's going to come to that cell wall and move that potassium ion into the plasma lamella and then through it and into the cytoplasm where it's released and then able to be used. And then that carrier is able to move another. So it's basically, this is just a protein that's moving back and forth, transporting those ions through active transport through the cells of the plant. Pretty cool. The translocation of sugars, on the other hand, which we're thinking of as the photosynthates that are produced through photosynthesis in the leaf, they are going to move throughout the plant through the phloem tissues, which can be downward, can be lateral or upward, from leaves to fruits or buds or other storage organs. In woody perennials, that phloem tissue is just underneath the bark following the development of the secondary vascular tissue. If that tissue is severed by girdling, such as in this case, that tissue above the cut is going to proliferate and the tissue below the cut is starved because of the movement of those photosynthates from the leaf downwards. And this is an important principle in the propagation of plants. Often, like with layering, for instance, we'll girdle it so that it accumulates there. It's going to make an area where it can actually develop a callus and then eventually develop roots. All the metabolites, the ions and water, are moving through plants through a variety of processes. Diffusion, which transports the ions and molecules slowly. Cytoplasmic streaming itself, which is active transport. It's faster than diffusion. Multi-directional mass flow of the material in the phloem. And then very rapid upward movement of water and the mineral nutrients through the xylem itself. The ways that water and the minerals move through the plant. Any questions on that? All right, so just a little bit about water and plants. We'll talk more about that as we get back into soils next week, and as we talk more about the mineral nutrition of plants as well. So on that note, we'll sign off, and we'll look forward to seeing you guys next week.
Okay. Have a good weekend.
You too.
Hunter, show up.
Hunter is here.
Okay.